Right, good morning. I'm Maggie Chen. I'm going to be your instructor this spring 2021 for your environmental science labs, and excited to meet you all. I am in my second year finishing up in the Master's of Science Environmental Management program here at USF, and this is my fourth semester teaching the labs. So I think I think that I've gotten like the gist and like the grasp on everything, but I do know that I tend to talk fast sometimes. So if ever I'm talking too fast, or if you have any questions about anything, you can just raise your hand, or you can just type into the chat to ask me to repeat something if you missed it, because I'm always willing to answer any questions that you may have. So that's a little bit about me. It seems like more and more people are finding the link and they're popping in, so that's great. Let me just take a screenshot of the participants list so I can take attendance later. So let me really quick just share my screen. Okay, let's first go over our lab page. So let me put this in the student view too. Okay, so just going over the Understanding Our Environmental Laboratory page. If you go to the main homepage, you'll scroll down and we'll see that this is our lab schedule. It's pretty, even though it says tentative, it's pretty much set. So last week we didn't have any labs. This week for February 1st, the week of February 1st, we're going over lab 1, data gathering, analysis, and reporting. So later on, after I go over like the course setup on Canvas, there's going to be a PowerPoint that I'm going over, and then an exercise in Excel. Next week for lab 2, we're doing understanding experimental design through SimBio. So it's basically setting up a lab procedure. What does that look like? How do we adjust variables? What do they mean? On the week of February 15th, we're not going to have lab because there's President's Day for that week. So then our lab 3 is going to be on the week of February 22, where we're going over Isle Royale population ecology using the same computer program, SimBio, where we're looking at populations between wolves and moose and how do predator-prey relationships affect each other. In the week of March 1, we're going over lab 4, population growth and ecological footprint, which ties into a little bit about population ecology and a nice transition from that, and also looking at our own ecological footprint, the resources that we take up, and what does that mean in terms of the world. And then a little bit of an intro to water resources, looking at our own the resources, the amount of water that we take up, which is going to lead into lab 5 on the week of March 8th, where we're looking and calculating the amount of water that we take up and doing a little bit of calculations. In the week of March 15th, there's no lab because that's spring break. The week of March 22, we're going over lab 6, water quality, dissolved oxygen, temperature, turbidity, looking more at water. What does it mean when there's a certain amount of oxygen? If it's cold, if it's hot, how does that affect the populations of fish or organisms that live in water? And then right after that, it's nice that right after spring break, there's lab 6, but then there's Easter holiday, so there's another week off, so there's no lab in that week. March 7th or April 5th, we're going over lab 7th, which is conductivity, salinity, desalination, which also ties into other water quality parameters. And moving on to the next week for lab 8, we're looking at a different type of water, moisture in the air. How does that react within our atmosphere, and looking at weather data, gathering and understanding weather data. How would we do that? And on the week of April 19th, there's no lab. It says semester check-in, but it's really to give you guys like a break to catch up on anything. If there are any labs that you needed some more help on, or anything like that. So there's no lab for that week of April 19th. For lab 9, we're going over the greenhouse effect. So CO2 concentrations, temperature, what did it look like over time? What does it mean for us as CO2 and other greenhouse gases increase over time? And then our very last week, or very last lab on May 3rd, is lab 11, Google Earth Pro. We're using Google Earth Pro, we're looking at the amount of land that different energy resources like coal, wind, solar, and how much land do they take up? What does it mean using these different types of energies? And the semester check-in is actually, this week off actually replaced lab 10. So that's why we skipped from lab 9 to lab 11. But then after that, there's no lab. I think this very last week, May 10th, that's when you start going into finals week. And then that's when we just start wrapping up for you all. So I think this semester is really well spaced out, where there's breaks where we don't have labs for certain weeks. So I think it's really well spaced out. But moving on from there, if we scroll down, for each of these labs, the background information, the pre-lab links, where you're going to turn in your assignments, you can find those in the corresponding lab 1, 2, 3 links down here. So if we're going to look at lab 1, we would just click into this very first link, and it would take us to this page where I sent out an announcement with the background materials and instructions for lab 1, but you can also find it here along with the pre-lab quiz link here. There almost always is going to be a pre-lab quiz for each lab, but I'll email you if there isn't. And additional information for each lab can be found if you scroll down a little bit more, like this video, which is what we're going to be looking at later on in this lab, along with other things like where you can turn in your assignments. So each lab is going to have one of these pages, and you can find that on the main homepage. But if you scroll down a little bit more, right underneath that, there are the instructor online learning pages, and you can find mine right in the middle here for Maggie Chen's online learning page. If we just go into here, you can find my contact information, so the email that you can reach me at. You can also just email me through Canvas, and you can also text me at this number if you have any questions. So lab policies for Wednesday AM and Thursday AM lab. So attendance on Zoom sessions is mandatory unless you have a time difference greater than 3 hours to US West Coast. If this applies to you, please email or message me in Canvas ASAP. So it looks like everyone made it. So, but if anything does come up and you find yourself moving for any reason or making any sudden changes, just email me, let me know, and we can work something out. A lot of students have taken this class asynchronously, so it can work. It's you just would watch the recordings after lab. So yeah, every single lab is recorded. But entering the lab session 5 minutes late will result in the tardy attendance mark. Entering lab session 15 minutes late will result in an unexcused absence. But again, if anything does come up, just email me as soon as you know that maybe you won't make it into lab, and then we can work something out and help you do your lab in another way. Have your camera on, microphone muted. If you do have any questions, you can just unmute or type it into the chat. Attend lab in the appropriate setting. Pre-lab quizzes are due at the start of lab, unless you have contacted me about asynchronous attendance. So pre-lab quizzes along with other assignments. So say for week 1, it's just going to be due the following week. So lab 1, pre-lab quizzes and assignments, or pre-lab quizzes would be due at the start of lab 1. Assignments will be available at the start of lab. So right now, Lab 1, that assignment is open for you all to do. Assignments will be due by the start of the next following lab session. So Lab 1, this assignment will be due by next week for Lab 2, at the start of Lab 2. You can have me regrade your assignments if you think that there are certain questions that maybe I misunderstood your answer, but then I could also just regrade everything again. So your entire assignment could be subject to regrading. Right, so this is the YouTube link with Zoom recordings and captions. Every single lab is recorded, the captions for that, and the recording for this, mostly it's always available like within that same day that we have lab. So later on in the day, maybe in a couple hours after lab ends, this recording will be uploaded to YouTube, so you guys can watch it over if you have any questions about any step along the way while you're finishing up your lab assignment. And then there's links to additional resources at the bottom. How to get Microsoft Office if you haven't already. Google Earth Pro download, which is for a lab that we're going to do more towards the end of the semester, and the Zoom meeting link. It's going to be the same link every single time that we meet, but that is basically it for my online learning page. Should anybody have any questions about either lab policies or any ways that you can reach me or anything like that? Okay, awesome. Great, so let me go back to our homepage and get started for Lab 1. So if we just click into Lab 1, the PowerPoint that I'm going over is available at the bottom of the Lab 1 page. So if you wanted to either take notes on the PowerPoint or if you wanted to refer to it later, the copy of the slides I'm going over is going to be at the bottom of this page. But let me just pull up the PowerPoint. All right, so Lab 1, gathering, analyzing, and understanding scientific data. Super important to have context for what we're looking at. So that means we have to make sure that our numbers are written in a way that's understandable, our units are right, and this PowerPoint was created by our lab manager, Darren Chen. So I'll just be going over this. So today we'll be going over unit conversions. How can we switch from one unit to another to make sure that in the situation that we're given, we're in the right units so our final answer is understandable. Then we're going over significant figures and scientific notation. How can we write our final answer in a way that shows which numbers are important? And then we're going over accuracy and precision. What's the difference between those? And how can we apply them to different situations? So unit conversions. Units describe the physical quantities that we're interested in understanding in environmental science and management. So there's a lot of different types of units. The basic units are length, volume, mass, and time. So an example of a length would be in meters, which can be abbreviated in lowercase m. An example of volume would be liter, which is uppercase L. Mass could be in grams, which is G, and time could be second, which is S. There's different types of units. So along with the basic ones, there's also mixed units, which could be like velocity, flow, or concentration. So for velocity, it could be meters per second, where it could also just be abbreviated for lowercase m to backslash lowercase s. So there's a lot of different units that we'll be working with, but these are some examples of them. And it's important for us to have units in our final answers so we know what we're looking at. So prefixes as multipliers. If we have different prefixes, we want to have a context to know what they are. So examples of prefixes are mega, kilo, deci, centi, milli, micro, and nano. They can be abbreviated as these single letters. So as an example, if we're going over centi, the abbreviation is lowercase c, and the multiplier of it is 0.01. So centi, if we're going to write it as a power of 10, would be 10 to the negative 2. This power of, this exponent, indicates how many spaces past the decimal point it's at. So if we're looking at the multiplier 0.01, if we go 2 spaces over past the decimal point, that would give us that negative 2. So 10 to the negative 2 means the same thing as 0.01, which would indicate centi. But now if we're going to look at mega, on the opposite side, where instead of a really small number, we're looking at a really big number, mega can be abbreviated as uppercase M, and it's a multiplier of 1 million. So if we're writing it to the power of 10, it would be 10 to the 6. And since there's no negative sign in front of this exponent, we know that it's going to be a really big number. And that's how many, this 6 is how many spaces past the decimal points to the left that this number is. So at the bottom here, if we're seeing mega, again, if we indicate mega as the 10 to the power of 6, we can rewrite this and we can have this context where 1.2 megatons would also just mean 1.2 times 10 to the 6 tons. These two definitions mean the same thing. And that's just something for you to keep in mind if you see prefixes that each of them have different multipliers, and it'll just give you a different context for that. So now moving on, if we're going to look at how we want to switch from one unit to the other, we can do that through dimensional analysis. So with dimensional analysis, we multiply quantity by the conversion factor to cancel out the units. So conversion factors are basically set like factors that equal each other. So say 1 meter is equal to 100 centimeters, where 12 inches is in a foot, things like that. So if we wanted to, as an example, convert 0.08 centimeters to meters, we can write it out first as 0.08 centimeters. We'll write that. We know the conversion factor, so there's 100 centimeters in 1 meter. And if we multiply that across, we're going to put the centimeters at the bottom of this fraction. So the centimeters from 0.08 cancel out with the centimeters here, and we would just multiply across. So 0.08 centimeters times 1 meter all over 100 centimeters. So the centimeters at the top would cancel out. We'd be left with the meter unit here, and our final answer would be 0.0008 meters. So this is how you would use our conversion factor to get to the final unit that we want. So unit conversion, why would we need to convert units? Usually numbers are reported with inconsistent units, and to understand our final answer and to have to calculate products or sums of numbers, the units have to be the same. So we can't add 12 centimeters to half a mile. What is this context for us? So an example of how we can do unit conversion is the length of a canal is 2.31 kilometers, and it's connected to a stream that is 150 meters long. So already we have two different units, kilometers and meters. So what is the total length of the water body? So we're going to have to convert one of these numbers one of these units to a similar unit so we can have that final answer. So we're gonna convert first the 2.31 kilometers to meters. We can do that through our unit conversion where we first write out 2.31 kilometers and we have our unit conversion of 1 kilometer is 1,000 meters. And this time, again, we're gonna want our units to cancel out where the unit conversion will have the 1,000 meters at the top of this fraction, the 1 kilometer at the bottom, and then the 2.31 kilometers, these units would cancel out here and we'll be left with meters at the end. So 2.31 kilometers times 1,000 meters divided by 1 is 2,310 meters. So we've converted the length of the canal from kilometers to meters. Now we can just add them together. So 150 meters for our stream. Since we already have it in meters, we'll keep it as 150 meters. And so our total length of the water body is 2,310 meters plus 150 meters is 2,460 meters. Great. So did anybody have any questions so far? Okay. Moving on to scientific notation and significant figures. Significant figures, what are they? If we're looking at a word problem or the situation that we're trying to analyze or do a calculation for, we want to know what figures or which numbers are important or significant for us. So significant figures are whole numbers between 0 to 9, and the non-zero figures are always significant. So as an example, if we have 9,683, these are all non-zero figures. So this means that this number has 4 sig figs. So, but what does it mean if we have zeros? So zeros, it's a little bit more complicated where there's different rules for which zeros are significant or not. So leading zeros that come before all non-zero figures and are not significant. So if we have, as an example, this number 0.0005, we're not going to count these leading zeros before this non-zero figure, the 5. So for this example, we only have 1 sig fig. Captive zeros are between non-zero figures and are always significant. So if we're looking at 15.40002, these zeros in between the 4 and 2 are captive zeros. So they are significant. Therefore, we have 7 significant figures. Trailing zeros that come after all non-zero figures are only significant if a decimal point is present. So if we have 32.1000, these zeros at the end, we don't really know what they mean if there's no final number at the end here. So we're going to say that they're not significant, and or that they are significant and therefore this number has 6 sig figs. And trailing zeros without decimal points are sometimes significant. So that means if we look at this number, 50,600 kilometers, we can say there can either be 3 sig figs, the 506, 4 sig figs, or 5 sig figs. So there is kind of like this vagueness that we can avoid by using scientific notation. And scientific notation, I'll be going over how you can rewrite a final number into that. But when a number has trailing zeros, it's just really vague and we're not sure how many sig figs there are. But finally, if there are exact numbers via counting or definitions, they're infinitely significant, but you don't have to worry about those sig figs. So as an example, when we did our unit conversions, we had 1 kilometer over 1,000 meters. You don't really have to worry about those sig figs. But These rules are also in the slides that are provided in the Lab 1 link. So if you need to refer back to them, they're available there too. So scientific notation. In the last slide, when we were looking at ways that we can get rid of vagueness in a final number, so we know how many numbers or how many figures in our final number is significant, we can do that through scientific notation. So it's a way to report numbers that are really big or really small, or that have a lot of zeros, so we can focus on the significant digits. So if we have 0.00001, we can rewrite it as 1 times 10 to the negative 5. So these mean the same thing, and there's the same significant digits. So this 1 here, we're just rewriting it here, and the negative 5, that negative just indicates how many spaces past the decimal point this number is. So how many significant figures is intended by 200,000? So that can be, it depends on how you rewrite it in scientific notation. So 2 times 10 to the 5 tells you that there's only one significant figure. 2 times 0.00000 times 10 to the 5 tells you that there's 6 significant figures. And 2.00 times 10 to the 5 tells you that there's only 3 sig figs. So it really depends on how you rewrite your number to indicate how many significant figures there are, which numbers are important. And that's going to depend on the context or the situation that you're given. So as another example, we see that the sun has a mass of 1.988 times 10 to the 30 kilograms. We know that this is a really big number with a lot of zeros in it, and it's much easier to write this number or write it this way using scientific notation than it would be to write it with all of these zeros at the end. And scientific notation is just an easy way for us to indicate really big, really small numbers and keep those in track when we're doing calculations or when we're trying to present our final number. So the breakdown of scientific notation. So again, we're looking at the mass of the sun. We're at 1.988 times 10 to the 30 kilograms. So this first part, 1.988, is the significant figures that we want to indicate. So it tells us how detailed our measurement is. The 10 to the power of 30 or 10 to the 30, this exponent gives us an idea of scale. So since we know that 10 to the power 10 to the 30 is really big, but if it's 10 to the negative 30, that's like past the decimal point, we know that's going to be really small. So the exponent is to give us an idea of scale. And finally, at the end, our kilograms are our units. So it tells us what we are measuring. Kilograms is very different from centimeters or from seconds. So our units are very important. So at the end of your calculations, please make sure that you have your units so we know what are we talking about, what are we looking at. So this is going to be your turn. So if we're going to be looking at scientific notation with the significant digits only, if we wanted to rewrite 0.00045 in scientific notation, how could we do that? I'll give you all maybe a couple of seconds and either you can unmute and say it or you can just type it into the chat.
For that first one, is it 4.5 times 10 to the negative 5?
Yeah, if you wanted to have two sig figs, you could write it that way. I think if we wanted to just keep it as 4, if we wanted to move the decimal point here instead of after the 5, it would be to the negative 4. Yes, so it depends on how many sig figs that we want, but if we wanted to rewrite this one, it could be to the -4. But -5, you would still have to add in four, 45.0, and that would give us 3 sig figs. So that's very close, very good. Okay, so if we wanted to write 4,500 in scientific notation, how could we do that?
4.5 times 10 raised to the power 3.
Yes, great. So that's how we could rewrite if we move the decimal point 3 places to the left. We would rewrite this as 4.5, and that would give us this 3 in the exponent for our power of 10. So great, perfect. Okay, so now there are other ways that we can also write scientific notation. So along with 10 to the power of whatever exponent, some calculators and some computers also report scientific notation with the letter capital E. So 700,000 can be rewritten in scientific notation as 7 times 10 to the 5, or it can be written as 7e plus 5. So if you have your scientific calculator like this, there's a function on here to get your power of E. Or if you use online calculators like Desmos, there could also indicate the 10 to the power of as a capital E. So we won't need scientific calculators for this lab, but this is just an example of where you can find this power or this capital E. And now if we're looking at a really small number, so 0.00007, we can rewrite it as 7 times 10 to the -5, or 7e minus 5. They all mean the same thing, but on certain computers or calculators, you would find it as an E instead. Okay, great. So sig figs in calculations. When making calculations using data with a specific level of uncertainty, it's important that you also report your answer with the appropriate level of uncertainty. So when you do calculations and you put your numbers in your calculator, it could give you more detail than you're actually given at first. So if you're given throughout your calculations, there's just more numbers than the instrument that you first used could give you, then you would have to just tone it back down, remember the context that you're given, and report it at the appropriate level of uncertainty. So sig figs are only important when reporting your final answer, but you should use all available digits, both significant and insignificant, during intermediate calculations. So significant figures and rounding, you do that at the end. When you're doing your calculations, you should use all of the numbers that you're given in your calculator and just round at the end so that your number is as accurate as possible. So this is sig figs and calculations. If we're looking specifically at multiplication and division, there's different rules for multiplying, dividing, adding, and subtracting. So if we're going to multiply, we're going to report sig figs equal to the quantity with the smallest amount of sig figs being multiplied or divided. So the smallest amount of sig figs, if we're looking at the 1.23, which has 3 sig figs, versus 4,567.89, which has 6 sig figs, we're going to be going with the smallest amount of sig figs, so our 3 sig figs here. So our calculator is going to give this big number with 8 sig figs. So we will round that up and report it with 3 sig figs, so our 5,620. But it's still a little bit vague, so we could rewrite this using scientific notation, and that would be 5.62 times 10 to the 3. And this would, using scientific notation, would clarify our sig figs, and now we have the 3 sig figs, which is the smallest amount of sig figs between the two numbers that we multiplied by. So multiplication and division, we're going with the lowest amount or the smallest amount of sig figs in our original numbers. Now, if we're going to be looking at addition and subtraction, we are going to go by the least number of decimal places in the values being added or subtracted. So if we're going to add 1.234, which has three decimal places past this number, or 567.89, which has our 2 decimal places, we're going to go with the least number of decimal places between these two values. So if we add them together, our calculator gives us this number with 3 decimal places, which makes sense, but we're going to report it with 2 decimal places. So our final number would be 569.12. So this is the sig fig rules for addition and subtraction. Now, if we're going to move on to accuracy and precision, which is what are these, what's different between these two, and how can we say what is accurate versus what is precise? So accuracy and precision. Accuracy is exactness, how true something is. So this is generated by calibration to a known standard or value. So if we're looking at a speedometer in your car versus a police radar gun, as an example, when you get your car, the speedometer, it's calibrated once. When you get your safety check, you don't calibrate it again. So you don't have annual, yearly, like maintenance things for your speedometer. So it's just calibrated that one time, and then that's pretty much it. So, but now we're looking at a police radar gun. They have to be calibrated like annually so that it holds up in court. So that means that the police radar gun is more accurate because of how often it has to be calibrated and how exact it is. So that means that comparing the speedometer in your car versus a police radar gun, the police radar gun is going to be more accurate compared to the one in your car. So how true that thing is accuracy. But for precision, or how precise something is, it's the quality of being well-defined or the level of detail presented. So the more detail that you're given in your instrument or in your final number, the more precise it is. So precision is generated by higher quality instruments and sensors. So the more sig figs, the more details that you're given, the more precise your instrument is. So if we're looking at a bathroom scale versus a laboratory analytical balance, your bathroom scale, maybe it could give you to 1 decimal place. Say if you weigh yourself and then you eat an Oreo and then you weigh yourself again, it's probably not going to change. You probably can't see how much of a difference that is. But if you're looking at a laboratory analytical balance, it gives us two, sometimes 3 decimal places, and it's super precise in that it's also very sensitive too, where you have like 3 glass slides and you have even like the wind blowing across it would change how much a thing weighs. So it's very sensitive. It also gives us a lot of detail. So the more precise something is, the more detail that it gives us. Where accuracy is how true something is and how correct. And it's also just generated by calibration. So those are the differences between accuracy and precision. They do sound the same, and sometimes in like the Webster Dictionary, they use those 2 words to describe each other, but just in a scientific context, this is what these 2 words mean. Now, if we're going to look at some examples, we can see for this first one, it's accurate, but not precise. So precision is the level of detail. Now, in this upper right corner, it's precise, but it's not accurate. Accurate is how true something is. And if we want to have that, it should be right in the middle of this circle. And this lower left corner, we can see it's neither accurate nor precise. And on the lower right, it's both accurate and precise. Just a visual example of that. So data precision. If you're measuring the length of fish to study the effects of water pollution on fish growth, how are these measurements different? And if we're thinking back to sig figs, and now we're just taking it as an example of data precision, if we're given 3 centimeters, 3.0 centimeters, and 3.00 centimeters, we can remember that precision is based on the amount of detail or the level of, or the amount of information given to us. So the more sig figs that we're given, the more precise the measurement. So that means that our 3.00 centimeters is the most precise number, the most precise measurement out of the 3. Okay, and now if we're going to be reporting measurements, so when you are reporting what you're measuring, the rule is to report digits given by your measurement tool. How would you report the fish length in each of the following 2 cases? Which measurement is more precise? So we see this fish down here. We're given 2 rulers, both in centimeters. This very first ruler on top, we can see that we can say that's around maybe 3.7 centimeters, almost 4 centimeters, but we're not too sure because the amount of detail that we would need to measure that is not really there for us to use. So this first ruler, we're not really too sure, but we can say it's more than 3.5, but less than 4 centimeters. The ruler at the bottom, along with centimeters, we're given millimeters too. So with this extra level of detail, we can say that the fish is actually 3.8 centimeters. And that means, just looking between the 2, that means this one is more precise. The amount of detail that we're given and the amount of detail that we can then report is more than this ruler. So between these 2, this ruler would be more precise. Okay, so that's how we would report measurements. Did anybody have any questions about any of the topics that we went over today? Okay. All right, let me go back to Lab 1 page on Canvas, because now we're going to be looking at measurements done by our lab manager and how would we use 2 different measuring tools, a ruler, your standard ruler, or a caliper. You don't need a caliper to do this lab, but it's just going to be shown to you how to use it, and we're going to be using data from that to make graphs later on. Okay.
In this video, we will be gathering raw data of leaf sizes using 2 different measuring tools, a ruler and a digital caliper. When the term raw data is used, it simply means data taken from a direct measurement, or data that has not yet been processed or run through any calculations. You will be using this raw data to calculate more advanced values and create graphs later on in this lab exercise. Here is our standard ruler. On one side, it measures English units in inches.
You're muted, Professor.
Sorry. Yeah, is there any problem seeing the video or can people? Okay, awesome. Okay.
And on the other side, it measures metric units in increments of centimeters. So each one of these numbered lines is your centimeter. We also see that our metric side has these smaller marks, and these are in increments of millimeters. So one of these small marks is a millimeter. And as we know, 1 centimeter consists of 10 millimeters. Therefore, we would say that this ruler is able to determine the length of an object to the nearest millimeter. Here is our digital caliper. It has jaws that can be opened and closed to measure the length of an object. It has a digital display that is controlled by an on-off button. And it can display its measurements in either inches or millimeters. And those can be changed with this top button. There is a third button that is labeled 0. This button is used to calibrate the caliper. The caliper is capable of giving us very accurate data, but first we need to be able to trust that it understands us. For instance, we can all agree on what the measurement of 0 millimeters looks like. That should mean that there is absolutely nothing between the caliper jaws and that they should be completely closed shut. So while we have that, the caliper jaws being completely closed, what do you know? Our display does not read 0, so that means the caliper does not understand what we mean by 0. It has its own idea of what 0 means at this time. So we can fix that by making sure, again, our caliper jaws are completely closed, and then pressing the 0 button, telling it that this is what 0 looks like. So that means what we have done is that we have calibrated the caliper to a known standard value, that value being 0. Now, these calipers are on the same page as us, and they are ready to go ahead and get measuring. Okay, so these are the 3 species of plant leaves that we will be measuring for our lab today. And right here, this is blue blossom, this is California bay laurel, and this right here is arroyo willow. And all 3 of these are native to California, to Northern California, and they can be found actually all over campus at USF here. So what I will be doing today is just demonstrating in this video measurement techniques for our ruler and our caliper with the California bay laurel. So in our procedure, what it outlines for us to do is to take the length and width measurements of the California bay laurel 3 times, and each one of those will be independently sampled, meaning that we're going to place our measurement tool at, say, the widest spot to get the width, and that looks like it is about 30 millimeters, and then we take it away. We remove the measuring tool and then place it back on the leaf and take another reading. And this looks like it is about just a little beyond the 3 mark there, so I'd say right there 31 millimeters. And differences like this can arise just from the positioning of the ruler or the measurement tool on the leaf. It can arise from just how we are looking at it, how we are viewing the ruler. Right now, I would ideally like to be my head right above the ruler, but I have the camera in the way, so it's a little difficult for me to get the best reading possible. Differences like this can occur just between different people measuring the leaf. If you're working with a lab partner and you're measuring the same leaf 10 times over each or something like that, you're definitely bound to get some differences, I would say, some differences between your measurements and your partner's measurements. Now, our final reading, our third reading on the width of this leaf is, it might be a little difficult to see on the camera, but it's just between the 3 centimeter mark, or the 30 millimeter mark, and the 31 millimeter mark right after it. But to my eye, I would just say that it looks a little bit closer to the 30 millimeter mark, so we will call it that. So our readings will say 30, 31, and then 30 again millimeters. Okay, now let's repeat the same process with our calipers. So we're going to once again be looking at the California Bay Laurel, and we are going to be using our calipers to measure the width and the length. So we've got them all zeroed out. They've been calibrated, they're ready to roll. So let's start, and our first measurement of width will read just around 31.1 millimeters. Take the calipers away. I like to close them to make sure that I'm not cheating. I'm using the same measurement again. And reopen them. And let's try to find the widest point on the leaf. Okay. And here I'm measuring at 30.6 millimeters. Remove the calipers to maintain independent measurements. And final reading, 31.2 millimeters. Here I've gone ahead and drawn a rough rectangle shape using the measurements of the leaf, and using the length and width measurements of the leaf. And this is how we're going to calculate leaf area. So with that in mind, take a look at the shaded in red space around the leaf, and you will use this visual aid to assist you with some of your post-lab questions. In contrast, here is an oval shape that I've drawn around the leaf using its length and width measurements. It's not a perfect oval, but as you can see, there is much less red shaded area between the oval and the actual shape of the leaf itself. So once again, use this in conjunction with the drawn rectangle and to answer some of your post-lab questions. So I'll leave you with that, and rest assured that the same process has been carried out with our blue blossom leaf as well as our arroyo willow leaf.
Okay, so that was how to use the ruler and the calipers to measure both length and width of these 3 different types of leaves. So now we are going to be working with the measurements from these, like each of the, both from the calipers and the rulers. And so the data for that, right underneath this video, there's this Microsoft Excel sheet with the data, and this link, if you get into this lab page, if you click on it, it's going to download this Excel sheet for you, and we're going to be working with that. So this is the link. I'll give you all a couple of seconds to just download this, but when you do get into your Excel sheet, it's going to look like this. So from here on this main page, if you make it a little bit bigger, oh, actually, I think I opened the wrong page here. Let me just download it with you. That one I was working with and accidentally deleted all of the numbers. So let me just make it a little bit bigger. So we are given our leaf measurements in millimeters, and on the left side, this left section, we measured with our ruler from the 3 different leaves, our blue blossom, Caliph Bay laurel, and arroyo willow. And on our right, we measured with the calipers, again, the 3 same leaf species, and measured 3 times for the length and width of each. So from here, we're just going to do some calculations to get used to Excel, but also so that we can see, we can just compare like precision and accuracy and answer some questions about those. So if we wanted to get the area or the leaf area for a rectangle, if we measured it if we were using our length and our width, we can do that by first clicking into this green cell. So, and we can start our equation by putting in an equal sign. And if you can't really see this green cell, you can also see your equation at the top here, this yellow, this white space, this formula bar. So for a rectangle, it's length times width. There's a couple ways that we can do that. First, we can just, after we start our equal sign, we can just select our length, our 44 millimeters, shift 8 to get our asterisk, and then select our 25 millimeters for our width. So length times width will give us a rectangle, and then you can just hit enter. And that will give us our leaf area. There's a couple of different ways along with just multiplying it like that. You can also just put in, we can start again our equation with our equal signs, just type in product, and different functions would pop up on a drop-down bar. And this very first function, product, would multiply this and get our leaf area for us. So we'll just select product. We'll click again on length, comma, width for our second number, and then we can just hit enter. And that would also give us the leaf area for that. So these are just 2 different ways for you to get your product. Either one works, but from here, we can also start getting our oval area too. So the equation for that, again, we're going to start our equation with an equal sign. The equation is pi over 4 multiplied by length times width, basically. So we can get our pi function by first putting in our parentheses, and then capital P and I for our pi, and then the function should pop up, and we'll just click on that pi function, and it'll start our parentheses for us. We'll just end it. We just need pi parentheses, and we're going to divide that by 4. So \4. And then we'll close this entire first part of our equation with a final parentheses at the end. And that is our pi with our double parentheses divided by 4. And now we're going to multiply this by length and our width. So you're, again, shift 8 to get our asterisk, our multiplied by. We'll select the 44 millimeters again, and we'll get that asterisk back in to multiply again by the width, our 25. And once we're at this stage, it's basically pi over 4 times length times width, and we can hit enter. And that will give us our leaf area for our oval. And one nice thing about Excel is that you don't have to continue typing it in over and over again. If you have your set values on the end here, if you just hover over your cell in the corner where there's like that green square, your your white plus sign would look like a black plus sign. And now you can just click and drag and then release, and it would autofill and do those calculations for you. And you can do the same thing for the leaf area on the side here. And you would just hover over that corner of your cell. When it's that black plus sign, you can just click and drag, and it would do those calculations for you again, using the formulas that you want them to do. So from here, now if we're just looking at this, we see there's a lot of decimal places, there's a lot of numbers going on, and we just want to put them in the right sig figs and maybe just put them in scientific notation. And how we can do that is just select the cells that we want to adjust. And after you select them, under the Home tab, in around the middle here where it says number, if you click on this arrow on this side, you can format the numbers that you've selected. So at the bottom, under general, there's number, currency, and all the way at the bottom, right above text, there's scientific. And if we select that, it'll put the numbers that we've selected into scientific notation. And here we have it. And now that we're here, we can also say that if we're adjusting things into sig figs and putting things into scientific notation, that we would want the length and width here in our 2 sig figs. Since we're measuring with the ruler and it only really gives us up to 2 sig figs, we would just select these numbers and adjust those. The way we can do that to get it to 2 sig figs is right underneath this, that same area, the drop down bar, to get it into scientific notation. There's these 2 buttons to increase the amount of decimal places and decrease the decimals. So we would just want to either increase, but we can decrease it and keep it to 2 sig figs. For Caliph Bay Laurel, we see that it's already in 2 sig figs. For the Royal Willow, there's just this one number that's in 3, but we can just adjust that and bring it back down to 2 sig figs. And from here, now we can also just adjust these numbers too on the side for our caliper measurements and keep them into the 3 sig figs, which our caliper gives us. Using the same 2 buttons up here, you can add or take out a decimal point or a decimal place. And the same thing for this. We'll just keep it to our 3 sig figs. The same thing for this one too. Okay. And one great thing about this, about Excel, is again, if you just select these cells and Command C, copy them, you're copying all of the formulas that you've already put in. And you can just click on the next cell that you want to put those formulas in. Those formulas went in, and then Command V to paste. And they would just do those calculations for you. So you don't have to keep on typing them in again and again. So we'll just Command V, and we can do that for the caliper measurements on the side here too. So we'll just click into this green cell, paste, and then Command V, paste, and we'll just paste that. So then all of the calculations that we want to do are auto-filled in. So now from here, we're going to want to just fill out this very last row for our averages. And the way we can do that is just click into that cell. We'll start our equation with the equal sign and AVE. And then after you type in those 3 letters, there's a drop-down bar that's just going to tell you the different functions. And the very first one is average. So we can just click into the average and then select the 3 yellow cells at the top where we want to get our averages from, and then hit enter. And that would give us our average. And from here, again, how we did with the green cells, we can just hover over this corner of our blue cell and then click and just drag, and then it would autofill these numbers for us. Again, we can keep these 2 in scientific notation right underneath the leaf area for rectangle and oval. So if we select these two cells, go back under the drop-down menu for different types of ways we can format our numbers, and just click on scientific. It would change it to scientific for us. Did anybody want me to go over any part of that?
Yeah, I have a quick question.
Sure.
Can I just see the formula for the oval and the green square is just one of those?
Sure. So, yeah, just making it a little bigger here, but if you can't really see it here, there's also this white formula bar that you can find it, but it's equals your pi function, so parentheses, pi, it's gonna autofill like
Yeah, I got it. Okay. Thank
Cool.
you.
No problem. Did anybody else have any other questions?
Can you do the averaging one more time?
Sure. Okay, so now we would just start, say we're gonna go on to like Calafe Laurel, we'll just start our equation with the equal sign. We'll just type in AVE and the function for average would just pop up, or you can just spell out average and then the function would pop up. You would click on this function here and then select the 3 cells that you want to get the average from. And then you would just hit enter. Awesome. Okay, and then we can just click and then drag that cell to autofill that formula. And again, adjust these to the sig figs that we want. So there's a lot more decimal places than we want here. So if we select these 2 cells and go back under that middle area, we can either take out, and we want to take out so we can have our 2 sig figs. And again, for these 2 leaf areas for rectangle and oval, we'll just select these 2 cells and change it into scientific notation. Was that good for everyone? Yeah? Okay. So from here, again, you can just autofill the other averages by selecting these 4 cells, Command C to copy them, and then just Command V, and you'll just paste them for every single space that we want to get our averages from. So then you don't have to keep on typing it in over and over again. And now from here, again, we'll just want to like adjust these numbers for our calipers to get our 3 sig figs. We'll just add in our 3rd decimal place, our 3rd sig fig. Okay, and once we're here, if we scroll a little bit to the right, we have our summary table, which should already be auto-populated with all of the numbers that we have been calculating and we've gotten. And I think it doesn't format it the way you want it, that we did in like the left side of this Excel sheet. So we can just format that again and keep this, the ruler part here, the average length and width, to our 2 sig figs. And then we'll have these average areas put them into scientific notation. It looks like they're already in 3 sig figs for our calipers for our length and width. So again, we'll just put the average areas here for the calipers in scientific notation. Okay. From here, we're going to be making 2 graphs, and we're just looking at our average rectangular and oval areas for both our rulers and our calipers. So what we're going to want to do is select these first cells. So from species, blue blossom, calife, laurel, royal willow. Once you select those, we're also just going to want to select these 2 columns. Way we can do that, and it depends on your keyboard, you can either press down on Shift or Command. For my keyboard, it's Command. So you're going to hold down Command and then select these cells for average rectangular area and average oval area, and then you're going to release Command. And once you do that, you can select cells that aren't right next to each other. So from here, if we're gonna make our chart, right next to the Home tab at the top, there's this Insert tab. And once you click into the Insert tab, in the middle of this toolbar, right next to Recommended Charts, there's also column charts that we can make. So we'll just click into column charts. There's 2D, 3D, 2D bar, 3D bar, but we're just gonna want this very top clustered column 2D chart. So we'll click into that and it'll give us our first clustered chart. We'll just make this a little bit bigger. And this is our chart for our ruler measurements. So it's great as it is, but we just want to add in some details that would make it even clearer for anyone looking at it. So we're going to want to add in our X and Y axes, and we're just going to want to adjust our chart title. How we can do that is once you've clicked into your chart, chart design would already pop up. But if it's not, say if you're clicking anywhere else on the chart on your Excel sheet, like this random cell, you can't really adjust it. So just click in on to your chart, and under chart design, all the way on the left-hand side of this toolbar, you can add chart element. Once you click onto that, there's this drop-down bar with all of these different functions or different things that you can add to your chart. But right underneath axes, there's axes title. So we're gonna want to add in our primary horizontal, our x-axis title, and then primary vertical, our y-axis title. So we'll just click and add our x-axis. We can adjust this and say these are leaf species. And now we can also just add in our vertical title. So back under add chart element, right underneath axes titles, and we already have our primary horizontal. We'll just want to add in our primary vertical, which is our y-axis title. And once that pops up, we'll just change this to say leaf area in millimeters squared. So if units are given to us, we're going to want to indicate those units on our chart. So in the summary table under average rectangular area, we're given millimeters squared. So we're also just going to put that onto our chart too. And now we can just change our chart title to something more descriptive. So different leaf measurements using a ruler. Something descriptive. It doesn't have to be exactly this, but you can just use this title if you want. But something that just says like what, or explains what are we looking at when someone is who didn't do this, what are they looking at when they're looking at this chart? So this is the chart for our ruler measurements, and we're going to make the exact same chart for our calipers. So the process is exactly the same. We're going to want to select these cells on the side and then hold down either Shift or Command, depends on your keyboard. I'll hold down Command and we'll just select these cells off to the side, and then I'll release the Command key to select these, our data. And again, under our Insert tab, right next to the Home tab, our Insert tab, and right next to Recommended Charts, we're going to want to click onto this very first tab for clustered columns, and this 2D column, clustered column, that's what we're going to want to make. Same process. And now it's just going to give us a different chart using our caliper measurements. So I'll just scroll over a little bit more, make our chart a little bit bigger. And again, we're just going to want to add in our X and Y axes titles. So once your chart is selected, chart design should automatically pop up. And again, under add chart element, we're just going to click onto that. On our drop-down menu, right underneath axes, we'll have axes titles. We'll hover over this, and we can add both our primary horizontal and primary vertical. Okay, so our primary vertical or our primary horizontal, our x-axis, we'll just select that. And again, the title is going to be the exact same, so we'll just write in leaf species. And now we can also put in our vertical title. So right back under add chart element in the corner, on our drop-down menu, again, hover over axes titles, and then we're going to want to add in our y-axis titles, our primary vertical. And we'll just change that again to leaf area in millimeters squared. So now this chart is for our calipers. You can again just rewrite it as different leaf measurements using a caliper or using calipers or something else, however you've been naming it. But these are our two Excel charts that we've made. And this is it for the Excel portion. Did anybody have any questions about how to make these charts? Okay, so this is it for the Excel portion. And now if we're gonna go back to the Canvas page and say we want to turn this in. Once you've completed your laboratory assignment, you can upload your Excel file here. So this link will take you to where you're going to turn this in. The Excel portion is basically done. And now you would just open a Word doc and answer these 3 questions and then submit your assignment. This isn't due until next week, the start of next week's lab, basically. So you can just finish it now and I'll answer any questions that you have. But this is how you can just turn that in. And that is basically it. If you all didn't have any questions, yes, somebody raised their hand.
Yeah, I was just wondering how many sentences you would want for each.
Yeah,
Yeah.
sure. Just like a couple of sentences. It doesn't have to be like a long paragraph or anything like that, but maybe like 2 or 3 sentences and just explain why do you think this is more precise? Why do you think this measurement is more accurate? And you can refer to the PowerPoints, which gives the definition some more, but yeah, just like a couple sentences. Okay. But that is basically it for lab 1. And if you have any more questions or if you wanted to finish like lab 1 before you leave today, you can just stick around. But thank you all for joining me and hope you have a good rest of your day. Okay.
Thank you.
Thank you.
Thank you. Have a good one.
Thank you. You too.
I have another quick question.
Sure.
So when we're answering those questions, are we just answering them right into the Excel and then just uploading?
You
Or-
can, but you can also just open a Word doc and just type those into a separate Word doc and then turn it in. But if you're gonna put
upload multiple files, we can upload multiple files.
yeah.
Oh, okay.
Yeah, I guess let me show you how you can do that. If you wanted to submit your assignment, so if you scroll down a little bit more, along with choose file, you can add another file.
Okay, perfect.
Yeah.
Thank you so much.
Yeah, of course, no problem.
Okay.
Bye.